Hi everybody, today we're talking about complete graphs. By definition, a complete graph, which we can write as k sub n, is a simple graph in which every pair of distinct vertices is joined by exactly one edge. And as a quick reminder, simple means our graph has no loops and no parallel edges. The most important thing to remember about complete graphs is that every vertex is adjacent to every other vertex in the graph. Let's construct some complete graphs starting with K1. K1 has one vertex, and because it has nothing to connect to and we're not allowed to have loops, it doesn't have an edge. When we add an edge and make K2, we now have two vertices and one edge. When we add a third vertex and connect it to the other two vertices, we form a triangle. When we add a vertex to make K4, it adds 3 new edges. Now we have 4 vertices and 6 edges. When we add our fifth vertex, we add 4 more edges to give us a total of 10. So let's stop and look at what we've done. Every time we add a new vertex, we have to connect it to every other vertex in the graph. What we find is when we add the nth vertex, we add n-1 new edges to the graph. That gives us two key formulas. The degree of each vertex in Kn is equal to n-1. Every vertex touches all others. Then the number of edges in the graph is n times n-1 over 2. Think of that as we have n vertices that are connected to n-1 other vertices in the graph, but because we don't want to double count the number of edges, we divide by 2. So let's say we wanted to know how many edges are in K10. We would start by finding the number of degrees for each vertex. That would be 10 minus 1, which is 9. Then the number of edges will be 10 times 9 divided by 2, which is 45. It would look like this: a graph with 10 vertices that are each degree 9. So if you're wondering why we're studying complete graphs, it's because they have great applications. We can use complete graphs in network design. That could show us fully connected topologies, as well as showing us the worst case for the number of link counts we will need. Connected graphs also show us round-robin play, meaning we could write out how every team meets every other team exactly once. And in general, complete graphs help us with relationship maps. This will allow us to capture all pairwise interactions within a system.